And we also know that y2 prime at 0 is MFA times L divided by EI times 1 minus cosine KL over KL over sine KL. Now, we used this definition of U before. So what is the definition of U? If you don't remember, what is U? U is what we call KL over 2, right? Remember, that's what we defined before. At the time when we have too many KL over 2, we just call this KL over 2 as this regular U. Then we go to the next page.
Professor, can you just go back for like a quick second?
Yeah.
All right, thank you.
Sure. So how do we use it? Now, because y1 prime plus y2 prime must be 0. We have the expression of y1 prime and y2 prime at 0. Then you can put them together. This way you can find out the expression of MFA, which is a fixed ending moment, that equals to negative WL cube 12 EI over 12 over 12. There's no EI. Let's not move too fast. Times this function, which is a 3 times tangent U minus U divided by U squared and divided by tangent U. So what is this end moment? And please do not mistake this end moment as just the end moment in the structural analysis, because that's not the case. In here, you recognize that there's U's participation, right? And because U is KL over 2, and what is K? K is the square root of P over EI. So if U is K dependent, K is P dependent. So when you see U, you see P. That means what? That means this part actually depends on axial load. This is P dependent. As long as it's P dependent, you understand that this part is the amplification due to axial force P. So that means when you have a beam column in this kind of fixed-ended boundary condition, subjected to axial force, the fixed end moment can actually be amplified too by the application of axial force, which is not surprising. Is another case to show us that in the buckling of beam columns, the behavior of moment becomes crucial because it becomes highly nonlinear. We have learned already that distribution of internal moment can be amplified by the application of an axial force P. So this is one way we will use it. In the next case, I think I will also show you from the slides. What about this? So how many cases we have studied? I just gave you the case for the uniformly distributed, right? And we spent a great deal of time to study the buckling of only end moments. So we know this case. And we also know this case. So in this example, I just combined these two. You remember from the example 1, we did this, right? So you already know this. And we already talked about this. So the next example, which is this one, I'm going to show you how we're going to combine these two. which is more like a review because we already solved for these ones. We already solved it. Now we just combine the cases that we studied before and put them in use. So let's come back to see this. And of course, if you already know the answer, just bear with me, all right? And so shall we call this case 1? Then we can call the next case 2. Okay, right? So in this case, we have fixed-ended axial force and another force, Q.
Professor is not showing that you're writing. Oh yeah, I'm sorry.
Is it showing?
Yeah, now it's good.
It just took a second to get up on the screen.
Ah, okay. And we know that this equals to the superposition of these two structures. But of course, let's not forget about the MFA and MFB. Fixed end moment at A and fixed end moment at B. That's what MFA and MFB mean. So the first one, we don't consider MFA and MFB. We just consider this load, Q, P, and the reaction, P. In this case, which already know the answer, plus this one. We have axial force, P, reaction P here, and MFA and MFB. Like this. So similar to the case I used before, because it's fixed-ended, you can choose to use either the deflection condition or to use the slope condition. Now, does anyone know that why would I use deflection condition? Why do I choose the slope condition here? You see, this is a slope condition. And if possible, I would recommend you to use the slope condition. Why? Because by taking the differentiation, you get rid of more variables. That's why. So if I can choose, there are two zeros. I can either choose deflection or I choose the slope. I always go with the slope. Don't go with the deflection. Because you have a deflection, then you will still have to deal with the constant term. If you can use the slope, all these constant terms will be dropped out. That's why we always go after slope. The same idea here. We're going to use this to be y1. y2. And the same thing that we did before, you have the expression for y1 and y2. So we're going to call it here. In the first step, we're going to say that what is the y1 and what is the y2? So for the y1 of x, that is this, q over p times the sine u. Actually, let me write it this way. I think it's better to write this way. Times the sine u over sine KL times sine KX minus Q over 2P times X. So this is a deflection. That's for Y1. Now for Y2, we already have it here, right? Which is from here before. So that's from the end moments. So in this case, if you go with Y1 prime and only deal with the X variables, that will give you KQ over P sine U over sine KL times cosine KX minus Q over 2P. And the next step, 61.
I'm sorry, can you just go back for 1 second again?
Okay.
Thank you.
Sure. For Y2 prime, this is step 2. We said because Y1 prime 0 plus Y2 prime 0 must be 0. For the same reason, theta A must be equal to theta B to be 0. And then we have this. We just plug in the expression that we had before, which is this one here. Now if you look at this, when you have x to be 0, cosine kx becomes 1, right? So that becomes just kq sine u over p sine kl. That is kq sine u over p sine kl minus q over 2p. So this is the first one. And the other one is just L over EI. That's the Y2 prime. So the first one here is Y1 prime. The second term is Y2 prime. That is 1 minus cosine KL over KL over sine KL times MFA. And this must be 0. So this part is Y2 prime, and the first one is Y1 prime, both at x equals 0. Why are we doing this? Because by using these boundary conditions, we can determine the unknown. And that is the foundation for slope deflection method that we use extensively in structural analysis. In this case, what is the value of MFA?